Modern Science and Technology Physics class. I'm NC Joshua. Today we'll be looking at heat capacity and specific heat capacity. What is heat capacity? Is the quantity of heat, the heat capacity of a body or an object is the quantity of heat that is required to raise the temperature of the body by a unit Kelvin. I reiterate again, the heat capacity of a body or a substance is the quantity of heat required to raise the temperature of that body by 1 Kelvin. Now take note of it. You see, I said there is the quantity of heat required to raise its mass, the temperature of the body, by a unit temperature. It's either 1 Kelvin or 1 degree Celsius. So you have it in different definitions. That's why I defined, apart from what I have on the board, that is the temperature required, is the heat required or the quantity of heat required to raise the temperature of the body by 1 Kelvin or 1 degree Celsius. Now, what is heat capacity? We use capital letter C to represent heat capacity. So heat capacity is equal to the quantity of heat. I use H as quantity of heat all over change in temperature. That is heat capacity. Now, what about specific capacity? It's just the same thing, but the only difference is that the specific heat capacity is talking about just a unit mass of the body. So, is the amount of heat required to raise the temperature of a unit mass of the substance by 1 degree Celsius or 1 Kelvin. That's what we also call a unit temperature. So it's either 1 Kelvin or 1 degree Celsius. So specific heat capacity is the quantity of heat required to raise a unit mass, and a unit mass is 1 kg. That's a unit mass, 1 kg of a substance or a body by a unit temperature. Now remember, this unit temperature can either be 1 degree Celsius or 1 Kelvin. Now, this is important. Why? Because it will help us know how to do calculations. What about specific heat capacity? We use small letter C to note specific heat capacity. And what is small letter C? Small letter C, which is specific heat capacity, is equal to heat all over M change in temperature. Now look at the two. This is specific heat capacity. This is heat capacity. Capital letter C for heat capacity. H over change in temperature. Now, what about small letter c, which is specific heat capacity? H over mass times change in temperature. Now, what is the SI unit for specific heat or heat capacity? Heat is in joules, temperature is in Kelvin. So it is joules per Kelvin. What about the SI units for specific heat capacity? It is equal to joules per kilogram per Kelvin. So this is the SI unit for specific heat capacity, while this is the SI unit for heat capacity. Now we're looking at the relationship between specific heat capacity and specific heat capacity. That's what we'll be looking at next. Now we are looking at relationship between big letter C, which is heat capacity, and small letter c, which is specific heat capacity. Now remember, small letter c is equal to H over M change in temperature. Now, if you look at this very well, you will realize that is this H over change in temperature is big C. So where heat over change in temperature equals big C, I will not say therefore small c, which is specific heat capacity, is equal to 1 over n times big C. So if you have that, it becomes small c is equals big C over M. Remember my capital letter C is specific heat capacity, while my small letter c is my specific capacity. So if I cross multiply, I will have is equal to mixes. So I have specific heat capacity times mass is equal to heat capacity. Now take note, very important. That means I can boldly say that my specific heat capacity is proportional to mass. But my heat capacity, I can boldly say that heat capacity is proportional to mass. Look at it here. Small letter c is our specific capacity, and big letter C is our heat capacity. So this is proportional to mass, while small letter c, which is my specific capacity, is inversely related to mass. So it means that heat capacity is mass dependent, but specific heat capacity is not mass dependent. Now, what do we have to see here? We have seen that the relationship between our specific capacity and our heat capacity is this, very important, is this, which we took further to this to show the heat capacity is mass related. Thank you. Now we're looking at measurement of specific heat capacity. Now there are two ways we can measure specific heat capacity. We have the mixture method and we have the electrical method. Now let's look at the mixture method. Now in looking at the mixture method, you must know the principle of mixture, which is also called the principle of calorimetry. What does this principle state? It states that heat loss by a hot body is equal the heat partner gain by a cold body. I reiterate, the heat loss by a hot body is equal the heat gain by a cold body. Now remember temperature differences. So the hot body has a higher temperature while the cold body has a lesser temperature. So when both bodies are mixed, now for instance, take a hot water now mixed with a cold water. Now there is something that will happen. Now the hot water is hot, extremely high, or at a high temperature. The cold water is below room temperature and is cold. Now what happens when you mix these two water together? Now the temperature of the hot water will definitely fall down. Now you cannot bathe with a extreme hot water of about at 100 degrees Celsius, a boiling water at 100 degrees Celsius. You won't dare bathe with such water. So also a water that is looking very cold, you want to bathe with such water too. So what do? You now mix the two water. Now the temperature of the hot water will drop while the temperature of the cold water will rise. Now both of them will meet at a particular temperature. We call that temperature equilibrium temperature. So when the hot body and the cold body is mixed, both temperature, one decreases because the hot body will lose heat, so the temperature will drop, while the cold body will gain heat and the temperature will rise. So both of them will now meet at a temperature called the equilibrium temperature, and we can call that temperature the mixture temperature. So now, if you understood what I just said, let's assume this to be theta hot, temperature of the hot. Let's assume this to be theta cold, temperature of the cold water, and let's assume this to be theta mixture. This is the temperature of the mixture. That's the equilibrium temperature. Now, if you understand these three temperatures, now ordinarily the temperature for theta hot is greater than the temperature of theta cold on its own because it's hot. But when we now mix the cold water and the hot water, what will happen to the temperature of the hot? The temperature of the hot will fall to the temperature of the mixture. What about the temperature of the cold water? The temperature of the cold water will rise. Now look at the two words, to the temperature of the mixture. So we are not saying that the hot water will lose heat to the cold water and it will fall. The temperature will fall to the temperature of the mixture. The cold water will gain heat and the temperature will rise to the temperature of the mixture. So that means that the temperature of the hot is greater than the temperature of the mixture. The temperature of the hot is greater than the temperature of the mixture. While the temperature of the mixture, very important, is greater than the temperature of the cold. Now, I want you to see it in case you do not understand. Look at this scale. This is 100 degrees Celsius. This is 0 degrees Celsius. Let's assume this is 5 degrees Celsius here. 5 degrees Celsius. So now this is for theta hot. This is for theta cold. So temperature of the hot is high. Temperature of the cold is low. Now I could not bathe with this water. Likewise could not bathe with this water. What did I not do? I now had to mix the two water together. So the temperature of the hot water will fall while the temperature of the cold water will rise. Now both of them now meet at a point. Let's assume where they are meeting now is 30 degrees Celsius. So this is now the temperature of the mixture. So now I can easily bathe with this water. Why? Because it's a warm water and it's good on my body. Now, so what am I trying to say? The temperature of the hot is greater than the temperature of the mixture, while the temperature of the mixture is greater than the cold temperature. So now what do we now have? We now have this as heat loss. That's what the law says. Heat loss is equals heat gain. So if heat loss equals heat gain, we'll say MC change in theta is equals MC change in theta. That's heat loss by the hot water is equal to heat gain by the cold water. Now, what about this? This is mass of water. This is specific heat capacity of water. This is the temperature change of water for the hot. For the hot. Now, what about for this? This is the mass of cold water, specific heat capacity of cold water, and the temperature change for the cold. For the cold. Now, this is temperature change for the hot. This is temperature change for the cold. Now, take note, water is water. So, the mass of the hot water and the mass of the cold water may change. I may have the mass of the cold water greater than the mass of the hot water. But the specific heat capacity of cold water and that of hot water is the same. It does not change. But the masses might change. But the specific heat capacity does not change. So now, specific heat capacity of water will cancel out specific heat capacity of water. So now, I want to make this show that this is for the hot, while this is for the cold. So now I will have it as mass of hot water, mass of hot water times temperature change of hot is equal to mass of cold water times temperature change of cold. Now, what is now this change in temperature? So I will have mass of hot water times what is the temperature change? Remember, the temperature change is the hot is changing to theta mixture. The hot is changing to theta mixture and the cold is still changing to theta mixture. So temperature change will be theta hot minus theta mixture. So it will now be open bracket theta hot minus theta mixture is equal to mass of cold water times what is the temperature change of cold? Is changing from theta mixture, theta cold to theta mixture. So this one is greater than this. So we'll now write it as theta of the mixture minus theta of cold. Once you understand this process, to solve questions in regarding the law of mixture is very simple. Now remember, heat loss equals heat gain, meaning the hot is losing heat while the cold is gaining heat. Now, what did we say? Specific capacity of water is the same thing, hot water, cold water. Specific heat capacity of water for the hot water and the cold water are the same. But the temperature change is where we have our major concern. And what is the temperature change for hot? Hot is changing to the mixture temperature. cold is still rising to the mixture temperature. So once you understand this temperature change, you can easily solve questions. So now we'll be doing some examples concerning the law of mixture. Now let's look at an example. What's our example? It says, explain the statement. The heat capacity of a body is 20 joules per Kelvin. The heat capacity of a body. Now remember, what is heat capacity? Is the amount of heat required to raise the temperature of the body by a unit temperature, and that unit temperature can be 1 Kelvin or 1 degree Celsius. So now it means that if the heat capacity of the body is 20 joules per Kelvin, it means 20 joules of heat is required. Remember, we said heat capacity is the amount of heat required to raise the temperature of the body by 1 degree Celsius or by 1 Kelvin. So now it means that amount of heat now is 20 joules. So 20 joules of heat is required to raise the temperature of the body by 1 Kelvin. That's what it means. Now look at example 2. It says, explain the statement. The specific capacity of a substance is 4.2 joules per kilogram per Kelvin. Now, what is specific heat capacity? The word specific here tells us about a unit mass. A unit mass, that's 1 kg or 1000 grams. So it means that 4.2 joules of heat is that amount. Now, first of all, what is specific heat capacity? Is the amount of heat required to raise the temperature of a unit mass or of 1 kg of the substance by 1 Kelvin or by 1 degree Celsius. So it means that specific capacity of a substance is 4.2, means 4.2 joules of heat is required to raise a unit mass or 1 kg of that substance. 4.2 joules of heat is required to raise the temperature of 1 kg of that substance by 1 Kelvin. That's what this means, and that's what this means. Now let's look at another example over here. It says a copper rod with a heat capacity of 585 joules per Kelvin is heated until its temperature changes from 35 degrees Celsius to 80 degrees Celsius. Stop. Calculate the quantity of heat supplied to the rod. Quantity of heat supplied. Now remember, big letter C is equal to quantity of heat over change in temperature. Now, what is our heat? Our heat becomes heat capacity times change in temperature. So quantity of heat will now be equal to, what's our heat capacity? 585 times, what's our change in temperature? Our change in temperature is 80 minus 35. So our quantity of heat is now equal to, so we have 26325 joules. That becomes the answer to the question. But there is a second question. It says if the heat capacity, if the specific heat capacity of the copper is this, find the mass of the rod. Wow. Now we have heat capacity of the copper. Now we have specific heat capacity of the copper. Now we are asked to find the mass of the copper. Now remember, so the big part of the question, what is our relationship? Our relationship is that specific heat capacity, which is small letter C, is equal to 1 over the mass times the big letter C. Remember this relationship? Very, very important. Now, what do I have here? So I have my specific heat capacity, which is 390. So I have 390 is equal to 1 over mass times, what's my specific heat capacity? My heat capacity is 585. 585. So what is mass? My mass will be equal to 585 divided by 390. So we have 1.5 kilograms. That becomes the answer to this question. Thank you. Now let's look at example 3. It says 10.8 kilojoules of heat is supplied to a meter of mass 800 grams to raise its temperature from 30 degrees Celsius to 70 degrees Celsius. Calculate the heat capacity. Now, what a distraction. Calculate the heat capacity. It means that our mass here is not important to us in this solution. So what is heat capacity? I will say solution here. Remember, heat capacity is equals heat over change in temperature. So what's our heat? Our heat is 10.8 kilojoules, meaning 10.8 times 1000. That will not be 10, 0, 1, 2, 1, 2, 3. So that becomes 10,800 over, what's our temperature change? Is 70 minus 30. So that will be equal to 270. Remember the SI unit is joules per Kelvin. Now watch this, it will not be joules per degree Celsius. Why? Because my temperature is in Celsius. So 270 joules per degree Celsius. Now, I want us to look at a case which is conversion of heat, conversion of heat, energy, conversion of heat. Now, if we have a waterfall, if we have a waterfall, water falling down from this region down, if we have such scenario, remember at this height, the energy we have at this height is called potential energy. So what is happening here? Remember we have heat is equal to specific heat is MC change in theta. Now if heat is this, and the energy we have is potential energy. So I can say, therefore, potential energy is equal to NC change in theta. Now, what is potential energy? Now, remember how I started it, a waterfall. This is more like a rock. It's more like a rock, and you have water falling from the top down to the base of the rock. Now, at this point, the energy at that point is potential energy, and you know potential energy equals mgh. So now the conversion of energy will be from potential to heat energy. So now I have this as mgh equals mc changing theta. So now what's my potential energy? Is mgh equals mc change in theta, where m takes off m, then I have my delta, my c, which is my specific heat capacity, is equal to GH over change in theta. Now, there are questions that we will solve using this particular concept. Now, let's see some examples. Now, let's see an example. It says a body of SHC, that's specific heat capacity, 90 joules per kilogram per Kelvin, initially held at a height of 90 meters. So the height 90 meters above the ground falls to the ground, assuming no heat loss to the surrounding. The rise in temperature of the body on striking the ground is dash. Now it means, recall, heat is equals mc change in theta. That's equation 1. And also heat, which equals potential energy, equals mgh, equation 2. So therefore, I will say mgh is equals mc change in theta. Now, m cancels at m because it's the same mass. Then we have, what's our g? Our solution to gravity is 10 times, what's our height? Our height is 90 meters, is equals, what's our c? Now remember that it is water, a body of, okay, a body of specific heat capacity is that. So they gave us our specific heat capacity to be 900 times our change in temperature. So what's our change in temperature? Is equal to 900 over 900. The answer is 1. Watch this. We're giving it in Kelvin, so it becomes 1 Kelvin. That becomes the answer to this question. Now, let's see a more tougher questions. A more tougher question. Now, what about this question? A piece of copper weighs 400 grams, is heated to 100 degrees Celsius, and then quickly transferred to a copper calorimeter of mass 10 grams containing 100 grams of liquid of unknown specific heat capacity at 30 degrees Celsius. If the final temperature of the mixture is 50 degrees Celsius, calculate the specific heat capacity of the liquid. Now, I want you to understand this question. What about the question? There was a copper, and this copper is hot. Mass of copper is equals 400 grams, which is now 0.4 kg. That's the mass of copper. Temperature of copper, theta of copper is equal to 100 degrees Celsius. And look at this, very important. Then this was not transferred to a copper calorimeter. Now it was transferred to a copper calorimeter containing a liquid. Now, what about this? When this copper gives out heat, it will give out heat to its surrounding. What is the surrounding? The liquid inside. And the liquid also becomes hot, that the container holding the liquid, which is the copper calorimeter, also gains heat. Now just imagine you have a kettle and you have water inside the kettle and you introduce on the fire. Now when the water starts boiling, the kettle also will be hot, just as the water is hot. So the water and the kettle gains heat. So it means that heat is lost by the copper, but heat is gained by the liquid inside and by the copper calorimeter. So now, if I want to solve this, I'll say heat loss by copper equals heat gain by liquid plus heat gain, heat gain by copper calorimeter. So take note of this, that this is how such a question is solved, because two things are gaining heat from the copper that is giving out heat. Now, so this becomes mass of copper, specific heat capacity of copper, and change in temperature of copper is equals mass of liquid, specific heat capacity of liquid, temperature change of liquid, plus mass of calorimeter, specific heat capacity of calorimeter, times temperature change of calorimeter. So take note of this. This is very, very important. This is of copper. This is mass of copper. So mass of copper, specific heat capacity of copper, change in temperature of copper is equal to mass of liquid, specific heat capacity of liquid, change in temperature of the liquid, plus mass of calorimeter, specific capacity of calorimeter, and change in temperature of calorimeter. Now, what about this? Now, the question is, what is the mass of copper? The mass of copper is 400 grams, which is now 0.4 kg, times what is the specific heat capacity of copper is 390, times 390 times what is the temperature change? The temperature change is changing from 100 to what is the final temperature? Look at it. If the final temperature of the mixture is 50, so it's changing from 100, 100 minus 50. This is for copper is equal to, what's it equal to? Mass of the liquid. Let's see, can we see the mass of the liquid? Yes, of masses containing 100 grams of a liquid. This is mass of the liquid. So mass of the liquid is 0.1 kg times specific heat capacity of the liquid. That's what we are looking for. Times what is the temperature change of the liquid? Remember, the liquid will stay, the liquid and the container will experience the same temperature change. Whatever is the temperature change that affects the liquid is what will affect the what now, the container. So where is this changing from? Now watch this. It's changing from, let's see, we said, let's read from here, then quickly transferred to a copper calorimeter of mass 10 kg containing 100 grams of a liquid of unknown specific heat capacity at 30 degrees Celsius. Now, this is the temperature of the liquid, 30 degrees Celsius. So, it's changing from 30 to 50. It was 30. On absorbing heat from the heated copper, it became 50. So it will now be 50 minus 30. Now this is for the liquid plus that for the calorimeter. Now let's see what about for the calorimeter. Mass of the calorimeter is 10 kg. 10 kg, 10 kg, copper calorimeter of 10 kg. So it will be 0.01 kg, 0.01. Now I'm dividing by 1000 to get it in kilogram. That's why I'm converting 10 grams to kg. So it becomes 0.01 times what is the specific heat capacity of a copper calorimeter. It is also equal to the specific heat capacity of copper because a copper calorimeter consists of copper. So it will still be times 390, then times what is the temperature change of the calorimeter? Remember, it's the same temperature change of the water. The water temperature change is the same temperature change of the container because it's the effect on the water that will be seen on the container. So it's the same thing as open bracket 50 minus 30. Now we now have this to be 7,800 is equal to, this will now be 2Cl 20 times this. Then we have this plus 78. So what do we now have next? We now have 7,800 minus 78 equals 2Cl. So this will now be equal to 7722 is equals to Cl. So my specific capacity of the liquid will now be equal to 3861, which is now joules per kilogram per Kelvin or degree Celsius. So we are using per degree Celsius. So that is the answer for this question. Now remember how I solved it. I had to know that copper is losing heat, the liquid inside is gaining heat, and the calorimeter also. Now this is the liquid and this is the calorimeter. Now the the calorimeter and the liquid are gaining heat. So heat lost by the copper is equal to heat gained by the liquid plus heat gained by the calorimeter. Now I want you to notice this, that there is one called the electrical method. It's very simple, electrical method. Now what about this method? The electrical method, remember that heat is equals mc change in theta. That's equation 1. Electrical heat is equals IVT is equals I square ROT and is also equals V square over ROT. All of these are electrical heat. So in solving electrical method is very simple. What about it? It will be MC theta, it can be MC theta is equal to IVT. It can be MC theta, change in theta is equal to I square ROT. It can be MC change in theta is equal to V square over ROT. Now, I want you to know that everything here is power times time. This is power. This is power. So it can also be MC theta equals power times time. It can be MC theta equals power. IV is power, electrical power. I square RO is electrical power. Then V square over ROT is electrical power. So these are formulas suitable to calculate for electrical method, and you can still use the same process to solve questions as regards electrical method. Thank you. Now let's look at some examples. We have example 1. It says 250 grams of lead at 170 degrees Celsius is dropped into 100 grams of water at 0 degrees Celsius. If the temperature of the afterward is 12 degrees Celsius, calculate the specific heat capacity of lead. Now they gave us specific heat capacity of water. Now please take note of this. We have a hot lead. This is lead. This is lead. Hot lead. Just follow me. This is hot lead. PB is for lead. Okay, we're not in chemistry class. This is hot lead at 170 degrees Celsius. Now we have water. Now we have water. We have water. The temperature of water here is at 0 degrees Celsius. Now, what will this be if lead is introduced into water? If lead becomes introduced into water, it means that the temperature of the lead will drop because lead will lose heat. Then why? The temperature of the water will rise because the water will gain heat. Now, if you understand this, what becomes our way of experimenting of solving this? We have heat loss is equals heat gain. Now, what is losing heat? The lead. What is gaining heat? The water. Now it becomes MC change in theta of hot equals MC change in theta of cold. Now remember, it will now become mass of lead. The mass of lead is 270 grams, 250 grams. Convert it to kilograms, it will be 0.2 kg times specific heat capacity of lead is what we are calculating for. So I'm looking for the specific heat capacity of lead times what is the temperature change. Remember, we said the temperature will change from 170 to the equilibrium temperature, which is now 12. So I have 170 minus 12 is equal to the mass of the coal. Now, what is the mass of water? 100 is the mass of water. So that will now be 0.1 kg times specific heat capacity of water is 4,200. 4,200 times what will be the temperature change? Remember, it's changing from 0 to 12. So it will be 12 minus 0. So I'll have it as 12 minus 0. So what we have here now will be the specific capacity of lead will be equal to 0.1 times 4,200 times 12 over 0.2 times 170 minus 12 will be 158. So what is now the specific heat capacity of lead will now be equals 59.49. Remember, the SI unit for this is joules per kilogram per Kelvin, but now it can be per degree Celsius because that's what we are using to solve. So this is how it is being solved. Now, mind you that there are other cases that you might involve the container, but that is not told us or asked us in this question because the heat absorbed or the heat gained by the water, the container also will gain the heat. So, but if this is a container that does not absorb heat, then it will only be the water that will gain heat. But if the container is a container that will absorb heat, it will be heat loss by lead is equal to heat gain by the water plus the heat gain by the container. I will show you a question as regards this soon after our examples. Thank you. Now let's see question number 2. It says a tap supplies water at 26 degrees Celsius while another tap supplied water at 82 degrees Celsius. So you see that this is already hot water while this is a cold water. Now it says if a man wishes to bathe with water at this temperature, so this is the final temperature. This is the temperature for the hot, temperature for the cold, and the temperature of the mixture. The ratio of the mass of hot water to that of cold is dash. Now, heat loss, heat loss, heat loss by hot water, by hot water, heat loss by hot water equals heat gain by cold water. That's the law of mixture. So what is the heat loss by hot water? So it becomes mass of hot water, specific heat capacity of water, then change in temperature of hot is equals mass of cold water, specific heat capacity of water, cold water or hot water, they are the same, then change in temperature of cold. Now take note, specific heat capacity of water can cancel out this. Then I now have it as the mass of hot times the change in temperature. What is the change in temperature of hot? Is theta hot minus theta final because the water will change from this to this. That's for hot. Why the water for cold will change from this to this because this is the final temperature he wishes to bathe with. So this is the temperature of the mixture. So it's now equal to mass of hot, mass of cold times what's the temperature change? Is now theta final minus theta cold. That is the temperature change. Now let's put this. What is the mass of now? Remember, what are we looking for? We are looking for the ratio of the ratio of the mass of hot to the mass of cold water. So it means let the mass of cold water come under the mass of hot water. Then this will now go under this. So I have mass of hot over mass of cold is equal mass of hot over mass of cold is equals theta final minus theta cold over theta hot minus theta final. That will not be ratio of mass of hot over mass of cold is now equal to, what's our theta final? Theta final is 40. Is 40 minus what's theta cold? 26 over what's theta hot? Theta hot is 82 minus what is theta final? Theta final is 40. So this will now be equal to, so this will be 14 over 42. So if you have this, will be 7, while this will be 2, 1, 7 here, 1, 7 here, 3. So the ratio is 1 ratio 3. That is the ratio. So the ratio of mass of hot to mass of cold is 1 ratio 3. That becomes the answer. Now let's look at solution 3. It says hot, the hot water tap of a bath delivers water at 90 degrees Celsius at the rate of 8 kilogram per meters. I want you to take note of this. We have for the hot at 90 is hot. We have for the hot, we have rate is equals 8 kilogram per minute. So that means 8, what that means is that rate is equal to mass over time. That's what rate is equal to here. Kilogram per minute means mass over time. Take note of this. It will help us very well. So that's the rate at which it delivers. Now the cold water tap of bath delivers water at 25 degrees Celsius at the rate of 15 kilogram per minute. Now the question says, assuming that both taps are left on for 4 minutes, calculate the final temperature. So if this is rate, now if rate equals mass over time, therefore I now have what is rate now? 8 is equal to mass over what is the time for the hot? The first time is the time that they left both of them was 4 seconds, so is over 4. Therefore, what is mass of hot? Mass of hot is now equals 4 times 7, 4 times 8, which is equals 32 kilograms. So this is mass of hot. What about for the cold? For the cold, what was the rate for the cold? The rate for the cold is 15 kilograms per minute. For the cold, rate equals 15 kilograms per minute. Now, what is rate? Rate, which is 15, is equals mass over time. What is the time? 4 minutes over 4. So, therefore, what is not the mass of hot? Therefore, the mass of hot is now equals 15 times 4. That will now be equal to 60 kg. So now, sorry, the mass of cold, not of hot. So we have the mass of hot. So I've used my formula for rate to be able to solve for the mass of hot and the mass of cold. And we'll now come back to heat loss by hot body or hot water equals heat gain by cold water. So from here, we can now apply our normal formula to solve the question properly. So now, what is our heat loss? So I have MC change in theta of hot, remember is the hot that loses heat, is equals MC change in theta of cold. Now, what is the thing that is most important is to know that both of them are water, hot water, cold water. So I have it as mass of hot water times specific heat capacity of water, then times what is the temperature change of hot. Remember, is theta hot minus theta final will be equal to mass of cold water times specific heat capacity of water. Then what is the temperature change of cold? It is changing from theta final minus theta cold. I've explained this to know how temperature changes are being done, because the cold will rise to final, the hot will fall to final. Now, since this will take all this, what is now the mass of hot we've solved is now 32 times, what is the temperature change? It's changing from hot. Hot is 90 minus, that's 90. What is the final? The final temperature is, okay, that's what we are looking for. Theta final is now equal to the mass of cold is 60 open bracket theta final minus temperature for cold is now 25 minus 25. So now what is not this? I have this to be 2880 minus 32 theta f is equal to 60 theta f minus 1500. So now take light terms, let this go here and this go here. So I have 2880 then plus 1500 is equal to 60 theta F plus 30 theta F. So this will now be 0, then this will be 8, this will be 3 carry 1, 3 plus 1, 4 is equal to 90 theta F. So this cancels this. Then we now have theta F is now equal to 48.6 degrees Celsius. So that's the final answer to this question. Thank you. Now let's see a question as regards example under electrical method. An electrical heater rated 15 volts and 40 watts. Now V is equal to 15 volts power equals 40 watts. And what's the next thing? Fitted into a metal block supplies heat to the block of mass 1.5 kg. Mass of block equals 1.5 kg. Now, and specific heat capacity of block is equal to 4600 joules per kilograms per Kelvin. Now calculate the temperature rise in the block if the current flow is 10 meters. If the current flow for 10 meters, so time is equals 10 minutes. If the current flows for 10 minutes. Now let's look at this. What is our mode of calculation? Electrical heat equals MC change in theta. Heat loss equals heat gain. So electrical heat equals MC change in theta. So I'll say electrical heat equals MC change in theta. Now let's see. What do we have as electrical heat? What are the parameters I have? Now remember I told you it is either it's IGT or it is I square ROT or it is V square over ROT. Everything is equals MC changing theta. So of these three, which of them is suitable? So now remember everything here is power, everything here is power, everything here is power. So I do not need this anymore because I have power already. So power times time is equals MC changing theta. So I'll use PT is equals MC change in theta. What is my P? My P is 40 watts times what's my time? My time is 10 minutes, which will now be 10 times 60 to convert to seconds is equal. What's the mass of the block? The mass of the block is 1.5 is the mass of the block times what's the specific heat capacity of the block is 4600 times change in temperature. Note that the change in temperature is what is referred to as the temperature rise. That's a change in temperature. So now, how can we solve this? So this becomes this, cancels out this, cancel out this. Then I have this. Okay, let me take this. So what do I have? I have change in temperature is now equals 40 times 6. That's 40 times 6 over 1.5 times 46. So change in theta equals 3.478. 3.478 Kelvin. That becomes the answer to the question. Thank you.